I'd like to thank the organizers for giving me an opportunity to present some of my work today. My lab studies breast cancer metastasis, and with all other cancers, breast cancer involves uncontrolled growth of cellular proliferation that leads to invasion of nearby tissues, travel through the blood circulation, eventually dissemination of these cancer cells throughout the body. The final stage of this devastating disease is termed metastatic colonization, and it involves disseminated cancer cells growing in vital secondary organs and destroying them in the lungs, brain, bones, and the liver. Luckily for us, though, this process is extremely inefficient, and that's thanks to our immune system. Cytotoxic T cells and natural killer cells are very good at identifying these disseminated cancer cells and killing them before they get a chance to grow. However, the very few cancer cells that escape this immune surveillance can become lethal later on. We know a great deal about the biochemical and molecular mechanisms that govern metastasis, but not so much about the physical mechanisms. And this is very surprising, because even the patients themselves can sense the physical stiffening of an abnormal growth during a self-examination. It turns out that physical stiffness comes from a network of extracellular matrix proteins that is built around the primary tumor itself, while the cancer cells within become softer. They become more compliant so that they can escape the confines of this cocoon, start squeezing through the stroma, and start the process of metastasis. But even when they start the process of metastasis, our cytotoxic T cells, the softening of the cancer cells, actually also help them evade the immune system too. And here's how it happens. Imagine you're trying to pop a balloon with your fingertips. In this analogy, your fingertips are your T cells, and that balloon is the cancer cell. If that balloon is soft, what happens is you have to exert a lot of force to be able to pop that balloon. If that balloon is now inflated, the surface is stiff, there's membrane tension, you can exert a little bit of force and pop that balloon and kill that cancer cell. Based on the very mechanical nature of this mode of immune surveillance, we call it mechanosurveillance. And we collaborate with biomedical engineers and cell biologists to understand fundamental mechanisms that cover cellular compliance, cell stiffness and softness. And we also collaborate with physician scientists and bioinformaticians to identify markers of mechanosurveillance in patients and in cancer health disparities. With that, I would like to thank all of you and thank our funders, our collaborators, my team, and of course our patients and their families.